we present our work, TriCoLo, Trimodal Contrastive Loss for Text-to-Shape Retrieval. Our method aims to solve the task of text-to-shape retrieval. Below are a few examples of the ground truth shapes with their corresponding text descriptions. Prior work targeted towards this task, such as y-squared sequence-to-sequence, proposes to use a variety of losses to align a shared embedding space between multi-view images and text. And parts to words proposes a complex matching scheme between parts of the 3D shape and individual word embeddings of the text description. Compared to these previous works, we show that our simple but effective trimodal contrastive loss is able to achieve better or comparable performance. Our overall model is shown as follows. We train our model to learn a shared latent space between voxels, multi-view images, and text descriptions. The voxels are encoded into an embedding with a 3D CNN, and a multi-view CNN is used to encode multi-view images. And finally, a BiGRU is used to encode text descriptions. We align the embeddings by pulling corresponding text and shape embeddings in the latent space, while pushing apart negative or non-corresponding pairs. During inference, we calculate the cosine similarity between the shape and text embeddings to select the top n objects which are retrieved from the dataset. We use the same normalized temperature scaled cross-entropy loss as in clip to pull together positive pairs and push apart negative pairs within a batch, using a symmetric bidirectional loss. Our complete trimodal loss combines the contrastive losses between all possible pairs between the three modalities. We evaluate our model mainly on the text-to-shape dataset from the text-to-shape paper. The dataset consists of shapes from the chair and table categories of ShapeNet, with several descriptions for each of the shapes. The complete dataset statistics are shown here. To validate the effectiveness of our trimodal contrastive loss, we conduct several ablation experiments. Here, bimodal I, or BiI for short, indicates the model trained with only contrastive losses between text and images, and BiV indicates the model trained with only contrastive losses between text and voxels, whereas the trimodals uses all three contrastive losses between the modality pairs. Here, tri-I and tri-V indicates that we only use the image or voxel embeddings when calculating the cosine similarity between text embeddings for retrieval, whereas tri-I plus V uses both the image and voxel embeddings averaged for retrieval. We can see that our trimodal model utilizing all the embeddings acquires the best performance across both retrieval metrics and shape similarity metrics, verifying the effectiveness of our trimodal contrastive loss. We can see in the next table that even our bimodal models are able to beat out most of the previous methods. Our trimodal model only loses against parts to words, which incorporates a more complex matching mechanism and requires additional part annotations to train. This highlights the effectiveness of our more simplistic trimodal loss, which achieves comparable performance. Here we show some qualitative results. The input text descriptions as well as the top 5 retrieved objects are shown. In the upper right-hand corner is the ground truth shape. While our model may not always return the ground truth shape, it returns plausible objects that matches the text descriptions. It is worth noting that although the dataset only has one-to-one mappings, in reality, one text description may match multiple shapes, and we can see that our model is able to retrieve objects that conform to the attributes mentioned in the text descriptions. We notice that our model fails on more fine-grained details such as wide armrest in the second row of examples. We also conduct manual analysis of 50 queries and count the different types of shape mismatches such as color mismatch or large shape errors. We can see that the trimodal model has the best performance while having the least amount of shape mismatches. We further evaluate our model on a more diverse set of shapes by introducing an extension of the original text-to-shape dataset with text descriptions for shapes ranging from 13 categories of ShapeNet. The number of sentences for each category are shown in the histogram. We see that our model also performs well on a dataset with more diverse shapes. Thank you for listening.